We finished, so last week we introduced protocol architectures, and we know about this 5-layer protocol architecture, the TCP/IP 5-layer stack. And we know that from the bottom up, the layers deal with transmitting signals, transmitting bits as signals, the physical layer. Data link layer, one thing it does is make sure those bits are delivered correctly to the other side of a link. So I have a link from my laptop into the wall and to some device downstairs. That's one link. Network layer deals with getting the data across multiple links across a network. One role of the transport layer is to make sure data is delivered correctly across an entire network. Even though the data link layer deals with an individual link and provides reliability, there can be failures across a network, and the transport layer has to deal with that, plus other things. And at the top, application layer deals with providing functionality specific to applications. We finished last week with some examples of addressing, so let's just recap on addressing. Each computing device has a network interface, and a computer can have more than one network interface. My laptop has a wireless LAN interface, an Ethernet wired interface. It also has a Bluetooth interface. So we say there's 3 different network interfaces for my computer. I normally just use one at a time though. At this stage I can't use any because I cannot connect. Each network interface has some hardware address associated with it. That hardware address is given based upon the LAN or wide area network technology being used. And that's usually related to the data link and physical layer. It's an address for communications across a link or within a LAN, the hardware address. Because there are different LANs and wide area networks across the world, using different technologies and different types of hardware addresses, to be able to communicate with 2 computers on different networks, we introduce a logical address or an internet or network address, the IP address. This is another address given to your network interface, which allows communications between computers which are on different LANs and wide area networks, but all use the same common internet protocol. That is for communications across the internet. So most working network interfaces will have a hardware address and an IP address. And we can think the hardware address is used to identify a computer on a single network, on a LAN or wide area network. An IP address is used to identify a computer inside the internet, say across the globe. And in addition, so that's to identify computers, port numbers are to identify applications on computers. Your computer may run multiple applications. Therefore, to identify which application we want to communicate with, the web browser, the email client, the instant messaging client, each application has a port number associated with it. So the port numbers identify applications on computers. So 3 different types of addresses. In addition, there are also some user-friendly addresses. IP addresses, hardware addresses, port numbers are used by computers to communicate with each other. But to make it easier for us humans sometimes, we have things like domain names, which are really just a human-friendly version of an IP address. There's a bit more detail than that, but we can map a domain name to an IP address. This is the thing that I can remember. The IP address is the part that the computer uses to communicate. So we have different types of addresses in the internet. We gave some examples last week. You can try on your own computer. There are just some examples of 4 commands which will run Most of them will run under Windows or Linux-based operating systems, Unix-based operating systems, including Mac. And they show different information about the configuration of your interfaces. ARP shows information about other computers on your LAN. And SLOOKUP shows information that maps domain names, like www.google.com to an IP address. And NetStat shows some statistics about your network communications. You can try them on your own computer. We showed them last week, or two of them at least. To finish this part on protocol architectures, we'll go through a bit more detailed example of TCP/IP operation. Firstly, a listing of some of the protocols used in the TCP/IP protocol suite. We know, all right, TCP, that's an abbreviation for a transport layer protocol. IP is a network layer protocol. So they are both two very important protocols used in internet communications. But there are many others. This is just a list of some of the others. So if we think of this as the network layer, we have the internet protocol, which is very important, but there are some other supporting protocols, and there are more than this. You don't need to remember what they do, what their abbreviations stand for yet. We'll see examples of them through different topics. But there are different protocols that support different functionality in the networking layer, especially routing. At the transport layer, which we can think of this layer here, there's TCP, but there's another one called UDP, which is much simpler than TCP, and there are several others as well. And at the top, the application layer, we have things like HTTP for web browsing, file transfer protocol, simple mail transfer protocol for email delivery, secure shell for remote logins, and many others that are not listed here. And down below, we think as the data link and physical layer protocols. So let's go through an example where a web browser accesses, or we use web browsing as an example application. And with web browsing, the simplest way to view it is that we have two entities involved, a web browser at the application level, a web browser and a web server. And the web browser requests some content, usually a HTML page from a web server, and the web server sends back that content, and it's displayed on the web browser's display. Here's my computer A. It has a connection to some network. Just call it the internet. And computer B. We'll say the computer A is running a web browser application. And computer B is running a web server. And the web server is just a piece of software running on that computer. You can run your own web server on your own laptop if you wish. It's just a piece of software running on that computer. And both computers are connected to the internet. We're going to omit the details of how they connect and what the internet looks like. We'll just say that, okay, they're connected to the internet. Both computers implement our 5-layer stack. We have the application layer, transport layer, network, data link, physical layer. Same in computer B. When we are web browsing, what the applications do is that when you type in a URL in your web browser and press enter, at step 1, the web browser creates a special request for the URL, or specifically the page you requested, and sends that in some message, a GET message, to the web server. When the web server receives this special message saying, I want to get the file in the directory test and the file name index.html, the web server receives that request. It checks in its directory on its hard drive, does it have the file index.html? If yes, and everything's okay, it sends back that file, or the contents of that file, in a response. The response includes some status information saying, meaning, I've received your request, everything is okay, here is the file. So the web server sends back in a message some status information and the contents of the file that's requested. And then when that's received at the web browser takes that HTML file and uses it to display something on the screen, the web page. That's the operation of web browsing, or a simple view of web browsing. Let's see if we have any internet access. That'd be useful. Nope. Okay, so let's do without the internet, or without the real live demonstration. So, we send a request, we'll draw that here, and it sends back a response. This is what we had on the previous slide, the GET and the page that's requested, and what comes back is the file, index.html, or the contents of that file. Let's see what happens from the perspective of the layers. And we'll focus simply on what's coming back, the file that's coming back. We'll look at, in detail, we're sending a message from the application at computer B to an application on computer A. What happens within the layers? We have our 5 layers inside the computer B, focusing just on the response. What happens is the web server application has the file that it wants to send back, the data, which is just the HTML file that's going to be sent back and displayed on the web browser. That's the original data that we want to communicate to the web browser, that file. The web server takes that data, the file, and the application layer, the protocol at the application layer, in our case it's HTTP, adds some extra information. That extra information is the header. On the previous slide, we'd think as this is the extra information. This is the header. It's some additional information as well as the data. In this case, the information, the meaning of the information is what is the protocol we're using, what version 1.1, some status number and some status message, meaning everything is okay. Another status you may receive, if we request a file that does not exist, you'll see something come back 404 not found. Most of you may have seen that on your web browser when you access a site that's not available or doesn't exist. That's just the status message from the web server coming back. In this case, it's okay. So the data is the HTML. The HTTP header is that information at the start, and combined we get the application message. That needs to be sent to the web browser on computer A. But to send it to the web browser, we actually deliver all of that to the transport layer. The data started at the web server. That application layer protocol, HTTP, added a header, delivered all of that to the transport layer protocol, TCP. TCP performs functions for making sure the data is delivered reliably to the other side. We won't see all the details of how it works, but one thing it does, it also adds some extra information to identify which application is this coming from and which application is it going to. That is, it includes port numbers in the TCP header. So it takes all of this, adds a TCP header, and delivers all of that to the network layer. And you can see the flow of what happens. Then at the network layer we have the internet protocol running, which simply tries to deliver the data to the next device in the network and eventually across the internet. It adds an IP header. Inside this IP header includes the source address of computer B and the destination address of computer A. That is the IP addresses of those two computers. When we send data through the internet, we need to identify where is that data going to, and that's done via an IP address. And that IP address is included in the header here. So you see this blue box contains the TCP segment. This IP packet or IP datagram has the TCP segment as well as the IP header. There's other stuff in the IP header which we'll see later. And then the network layer sends that to the data link layer. And in our example, let's say we're using Ethernet, which is just the wired LAN commonly used at the data link layer. This is all inside computer B. Nothing's being sent. It's just all communications inside the computer between software processors inside the computer and eventually hardware in the computer. We take the IP datagram. In Ethernet, it in fact has a header. It also has a trailer, something at the end. There's no difference really, it's just placed at the end of the packet. It includes a checksum to check that there are no errors in the packet at the receiver. And a header includes the hardware address of the computer and the destination hardware address. Data link layer delivers that to the physical layer, which really treats it as a sequence of bits. The physical layer thinks, okay, this is a sequence of bits that I need to transmit across a link. So the physical layer has a sequence of bits, whatever they are, representing all of this information, and transmits a signal across the link, the cable it's connected to. This is some signal, some electrical signal, for example. Don't worry about the shape, it's just representing some sinusoid which is representing electrical signal being sent across the cable to the next computer attached to the computer B. So the physical layer has bits that have made up from all of the data that's come from the higher layers and transmit some signal across the cable. I've drawn a cloud to represent an internet here. It may be many different links. At the other endpoint of this link, if there's a computing device here, it would receive that signal, convert it back to bits, possibly look at the Ethernet frame and the IP datagram, and then send it on using the same approach to the next device. And it goes across the internet until a signal is sent to computer A. And at computer A, we can look at this diagram but go the other direction. We receive some electrical signal, say. We convert that back to bits. We must know this mapping. What does this signal represent? Does it represent a bit 0 or a bit 1? And we'll spend an entire topic looking at how can we encode zeros and ones as different sinusoids, as different signals. Computer A receives a signal, converts it back to bits, sends those bits to the data link layer, which would represent all of this information. Data link layer checks whether what it's received is correct. If everything's okay, removes the trailer and header and sends this to the network layer. Network layer checks, okay, I'm the destination. Remember, this is at computer A. Physical layer received a signal, sent bits to the data link layer. Data link layer checks everything's okay, removes the header and trailer, sends just the blue box, the remaining data, to the network layer. Network layer checks, okay, I am the destination of this IP datagram. The destination address is my address, therefore it's to me. Take what's inside this blue box and send it to the transport layer. Transport layer does the checks, whatever it needs to do to check whether it's received the data correctly. If everything's okay, removes the header, sends the data inside to the application layer. Application layer, which is HTTP, again, checks what it's received, removes the header, sends what's inside to the application, the web browser. The web browser then has this data. Remember, from computer B, the data was the HTML file, the thing that we want to download. We've received that data at the web browser. The web browser would now display it on the screen using the markup to display whatever text is in the HTML. What this is showing is how data flows through the layers from the transmitting computer to the receiving computer, and how different protocols take the data from the higher layer, encapsulate that into a packet, add a header on, possibly a trailer, send that to the lower layer to deal with. We didn't show all the details of how does TCP check that it's correct? How did the network layer make sure it gets across the right path? How did we convert bits into signals? We didn't show all that information. That's what the entire course, or the rest of the course, will show. So to deliver just this piece of data, we had to go through those 5 different layers, add all this extra information, transmit a signal across one link, do it all again across the next link, and again and again until it gets across the final link here, remove all those headers and trailers until we get the original data back at the web browser. And then we've successfully delivered that data from B to A. you'll recognise that to deliver that piece of data, we need to add some extra information to it. That increases the overhead in our communications. And towards the end of this lecture, we'll do some calculations based upon this and see how much overhead it may introduce. So we will return to this diagram towards the end. That was just the web page going from server to browser. Then you get the web page displayed on your browser, then you click on another link, and the same procedure has to happen to send the request to the server again, and the same procedure for the server to send the web page back to the web browser, and so on. Let's finish on protocol architectures, and then we can look at something different and do some calculations about performance. Where is all of this implemented? Where is it inside your computer? Well, a rough categorization of where the layers are implemented is shown here. Application layer protocols implemented in end-user applications, user processes. Web browsers, instant messaging applications, voice applications can implement, so in software, the application layer protocols. So if you look at the source code for Firefox, you should find their source code which implements HTTP. Sometimes it's included in the web browser, sometimes there's an additional library to bring it outside the web browser. Application layer protocols implemented in end-user application software or processes. The transport layer and the network layer are generally implemented inside your operating system. Inside these layers are protocols commonly used by many different applications. So when you install Windows, one piece of software inside there is software implementing different transport layer protocols, TCP, and software implementing IP, the Internet Protocol. So most operating systems implement protocols in these two layers inside them. And the last two layers, the data link layer and physical layer, generally implemented on hardware and to some parts on software in your network interface card. So although you may not see it in your computer, there's a card or a set of chips which represent your network interface card. They are implementing how to transmit signals and how to check the bits that are received, the data link layer and the physical layer. That's a rough separation of hardware, or the network interface cards, the operating system, and at the top, user processes. So if you wanted to write your own application protocol, that wouldn't be too hard. You can write an application. If you wanted to modify how the Internet Protocol worked in your computer, that would be harder because you'd need to modify your operating system. In some cases, it's impossible if you don't have the source code. If you want to modify how your physical layer works, that's almost impossible for you because you need to implement that in hardware. It's much harder for an end user like you and me to do, possible for larger companies. Next semester in your networking lab in ITS322, I think, or 332, you'll implement your application layer protocols, a simple web browser, for example. So that brings us to the end of protocol architectures. Let's spend some time looking a little bit about internet applications, classify them, and focus on how do we measure their performance? What do we care about? Because throughout the rest of the course we'll use these performance metrics to evaluate protocols. What do we mean when we say internet applications? Well, first, a standalone application. I don't know, some photo editing software that you just run on your computer. It just works on your computer and it does everything it needs to do running just on your computer. It has some user interface and we say some application logic. There's some source code that implements how you interact with that application, and there's some code that implements what that application really needs to do, the logic of the application. An internet application or a networked application, or possibly a distributed application, has some user interface, some application logic, but the application works, it provides the service by communicating with other instances of that application. So it has some communication mechanisms as well. We say web browsing is an application which involves a web browser communicating with a web server. It has some user interface. The web browser has a user interface where you can click on buttons and it will respond to that. It has some logic that the web browser, when it receives a HTML page, it parses that page, it looks at the HTML and sends it to the interface to display on the screen. And it has some communication mechanisms to send a request and to receive a response back. That's what we're interested in, the communication mechanisms. So we could say that in terms of internet applications we have the traditional data-based applications. Not a database, but data-based. That is mostly involved with transferring data between different entities. File transfer, email, web browsing, remote login, database applications, and many other applications. These applications use the communication mechanisms to transfer data between different entities on the network. The other side, we can say that we have multimedia or real-time applications, audio and video streaming applications, interactive audio and video, that is voice calls, video calls, gaming applications, collaborative applications where you share your desktop between different users. I think you've all used these different types of applications. In terms of performance, roughly, these applications, accuracy is key. In these applications, timeliness is important. Remember our three measures? Delivery, we want to make sure we deliver the data to the correct destination. That applies to both applications. Accuracy and timeliness. Accuracy, if I send a 1,000 kilobyte, a 1 megabyte file from computer A to computer B, then that exact sequence of bits that was sent should be delivered at the computer B. What was received should be the same as what was sent. That's 100% accurate. That's what we need in these applications. If I transmit a web page from computer B, what computer A receives should be exactly what was transmitted. 100% accurate. We care about timeliness, but it's not as important with some of these real-time applications. You're talking to someone on Skype or MSN, you're having a chat over the internet. From when you speak and the microphone takes your voice, converts it into bits to be sent across the internet, until when they are received at your friend's computer and converted back to audio and played on the speakers, you want a very small delay, a very small time from when you speak until when they receive it, on the order of hundreds of milliseconds. If I speak and it takes 10 seconds to deliver that to the other side, then they will not be able to converse. You will not be able to talk with someone if there's such a delay between the person talking and the person listening. Because one person will say something, the other will be waiting the other won't hear anything, so they'll start talking, and then they'll start to cross over and talk at the same time. So that's an example of voice calls. Similar streaming applications. You press play on your YouTube video. You may tolerate some delay to start, but once it's playing, you don't want it to start and stop every 5 seconds and freeze and start and stop. You'd want smooth playback so you can watch the video in real time. So in these applications, we care more about timeliness, especially the delay, the time it takes to get the data from one computer to the other computer. We care about timeliness a little bit in these applications, but not as much in general. And in some of these applications, we can tolerate an accuracy of less than 100%. We can send some video across the internet. So we have some video stored on the server, and we're going to stream it to the web browser. What the web browser receives and plays back on your screen may not be 100% of what was originally at the web server. Even if we lose some parts of that data, we can still play back the video. Because some parts of that data just may represent a pixel or several pixels at the top of your screen, which are displayed for 1/10 of a second. You will not notice whether those pixels are the wrong colour or not, and therefore you can still view and get a satisfactory experience watching that video. So with some of these applications, even if the accuracy is not 100%, we can still use them. So with these, we need 100% accuracy. That's an important difference. So to finish this topic, we're going to look at several measures of performance. How could we measure, especially timeliness, and other metrics that we have in a communications network to evaluate how good it is, the performance. And we'll go through some examples to illustrate these. First one, so we'll go through, I think, 5 performance metrics. We'll list 5 performance metrics, and we'll see most of them throughout the semester we'll see are quite important as evaluating different protocols. First one, which we won't say much about, is referred to as bandwidth. When we transmit our signals, we're sending some electrical or electromagnetic signals. They utilize some frequency of a spectrum. And it turns out that we cannot use an unlimited set of frequencies. There's only a limited range that we're allowed to use, or that we can use, and therefore it generally costs more to use a larger set of frequencies, a larger bandwidth. Bandwidth is measured in hertz, frequencies are measured in hertz, and we normally want to minimize the bandwidth we use to transmit our signals, and also sometimes to use a bandwidth in a particular portion of the spectrum. I'm not going to say any more about this because the next topic will go into that in detail. It's harder to give examples without explaining it over 1 hour. But that will be one important performance metric, bandwidth. Another one that you would be familiar with is data rate, the speed at which we send data, and the number of bits some communications channel or some network or a link can transmit. So you may pay for an ADSL link for home internet access, and you may pay per month some amount, and that gives you a 6 megabit per second link. We'd say that's the data rate of your link. The link is the communications channel. That's the link we have. And you can send 6 a maximum of 6 million bits every second, 6 megabits per second. We'd say that's the data rate. In other words, sometimes it's referred to as the capacity, the maximum amount of that can be transferred across that link, or the bit rate, the rate at which we can send bits, simply the data rate. Often we want that to be as high as possible. You want your ADSL, for the same price it would be better to have a 12 megabit per second link than a 6 megabit per second link, because you can transfer the data in those previous applications faster. You can download files faster, you can stream higher quality videos, therefore generally users want a higher data rate. If you pay for your 6 megabit per second ADSL link at home, does that mean you can download a file and the download speed would be 6 megabits per second? Well, probably not. If you download a file, you'll find that the download speed is much less, or less than 6 megabits per second. There are overheads that are incurred when we transfer data. So another measure of performance is throughput. Data rate is the number of bits we can transmit across a link or a network per second. Throughput is the rate at which we can transfer useful data across a link or a network, also measured in bits per second. If we go back to our example of the TCP/IP layers, we had our real data that we wanted to transfer across a network, but to send that real data we needed to add these headers, trailer, and transmit all of them. So we'd say that these headers are some overhead incurred. To transmit this data, we actually have to transmit all of this. So there's some extras that we need to transmit. So even if my data rate is 1 megabit per second, the rate at which I deliver data may be much less than 1 megabit per second. Maybe it's 900 kilobits per second. That would be the throughput, the rate at which we deliver the real data across the link. Let's see if we can do a calculation of, a very simple calculation of the throughput in this case. I'm going to introduce some numbers for how big is the HTTP header, how big is the TCP header, and so on. So we can do some simple calculations. In some cases the numbers are real, in some cases they're made up, so I can add up the numbers easier. Let's list them. I'll get this right. So we need to first to calculate, we want to calculate if we send some data of a particular size over a link of some with a data rate of say 1 megabit per second, what is the throughput of sending that data? So that's the scenario we have for this simple example. Two computers connected via one link. Over there we had possible many links, but to keep it simple, one link, and the data rate of that link is 1 megabit per second, which means we can transmit bits onto that link at 1 million bits per second. Every second we can transmit 1 million bits, and B will receive 1 million bits every second. That's the capacity of that link. We can't send any more. That's a characteristic of the technology we use there. But in fact, we have our original data and we add all these headers. And then we send all of that, which represents all of the headers, together. So in fact, we can say each protocol adds some header of a particular size. And that's normally, the size of that header is part of the specification of how the protocol works. It's normally fixed or within some range. I'm going to give some numbers to the size of these headers. Let's write them down. Some of them are based on real data or real sizes of headers. HTTP, we're going to say, takes the data and adds 48 bytes to that. That 48 bytes contains what we saw in one of the previous slides, this thing like HTTP/1.1 OK and other stuff. TCP header is 20 bytes. 48, this is a B. And I will try to use, and throughout the course you will use, uppercase B, meaning bytes. And we'll use lowercase b to mean bits. 48 bytes. 8 bits to a byte. TCP has a 20-byte header. So the length of this header is 20 bytes. IP header, 20 bytes as well, and that's in real life, the size of the header is 20 bytes. Ethernet adds a 14-byte header as well as something at the end, 4 bytes of trailer. The physical layer, which is also part of the Ethernet standard, adds some extra bits at the head as well, 16 bits to the front of the Ethernet frame. So if we take this sequence of bits, the physical layer adds another 16 bits at the front, or 2 bytes. Let's say our web page that we want to download, that is, we've requested a web page. The size of that web page is 10 kilobytes. Write it here. 10 kilobytes is the size of the file. And throughout this course we'll use kilobytes, meaning 1000. Not 1024 that you may see on hard drives, but the decimal value 1000, 10 to the power of 3. 10 kilobytes is 10,000 bytes. That's the size of the web page that we've requested and we're trying to transfer from the server to the web browser. That is the size of this data. Our link supports a maximum speed of sending 1 million bits per second. What is the throughput of delivering this web page across that link? That's what we want to know. The throughput is the rate at which we can deliver the real data, that is that web page, from computer B to computer A, from the server to the web browser. Well, let's see how much how many bits we actually have to send across the link. We have our file, which is 10 kilobytes in length. 10,000 bytes. Do everything in bytes for a calculation. That's the size of our real data. On top of that, the application layer adds a 48-byte header, the HTTP header. So we take our data. We'll also need to transmit those 48 bytes across the link. We'll need to transmit the 10,000 bytes of data plus the 48 bytes of header. And TCP adds on top of that its 20-byte header. IP, a 20-byte header. And so on. That is, if you can see there, I'll get out the road. Each layer adds a header on, or a trailer, and that's just the total size that we have there. We have our 10,000 bytes of data, 48 bytes of HTTP header, 20 bytes of TCP header, 20 bytes of IP header. Ethernet has 14-byte header plus 4-byte trailer, so that's 18 bytes. And the physical layer has a 2-byte header that it adds, or 16 bits. Sum that up. What do we get? (10,108 bytes). So to transmit that original data of 10,000 bytes from B to A across our single link, we have to transmit 10,108 bytes across the link. That extra 108 bytes are the headers and trailers. They are overhead in our communications. We need to do it because they are part of the protocol. But it means that 108 bytes of extra, it wastes some of our time of not transmitting real data. Let's see how much. Total amount of data that we send is, in bits, 80,864 bits. We can either do the calculation in bytes or bits. As long as everything's in the same units, it's okay. Our data rate is given in megabits per second. That's 1 million bits per second is the rate at which we can send. How long does it take to transmit that? We've got 80,864 bits. How long does it take to transmit all of those bits across our link? Does anyone calculate that? Calculate the time to transmit that across the link. answer for me? One million bits per second. One million bits per second, one bit. Therefore, we can send one bit. See if we can see this. 1 million bits in 1 second, therefore 0.000001 second to transmit 1 bit, which is 1 microsecond. This is mu, this is not m. It's microsecond. 1 microsecond to transmit 1 bit, 2 microseconds for 2 bits, 1 second to transmit 1 million bits. 1 microsecond to transmit 1 bit, we need to transmit 80,864 bits, so we can calculate the time to transmit. (80,864 microseconds) or 80.864 milliseconds or 0.08 seconds. So we can calculate the time to transmit that data. So that's the total time it takes us to transmit all of those bits across the link. What is the rate at which we're delivering useful data across the link? Because not all of those bits are useful from the user's perspective. From the user's perspective, what was useful was our original data of 10,000 bytes. Doing, from the user's perspective, we are transferring 10,000 bytes, that is the file, in a time of 80.864 milliseconds. So that gives us a rate. We're sending 10,000 bytes in 80.864 milliseconds. As a rate, 10,000 bytes divided by 80.864 milliseconds. And that will give us our throughput. just be careful when we're converting between seconds, milliseconds, microseconds. 10,000 bytes in 80.864 milliseconds, 10,000 times by 8 to get bits, divided by 0.0806864 seconds. I just converted to seconds down here. 10,000 times 8 bits in 0.080864 seconds gives us 989,315 bits per second. That's our throughput. That is the rate at which we deliver the useful data across that link. The rate at which we're sending all of the data across the link is 1 million bits per second. But the rate at which we're sending the file, the useful data across the link, is slightly less, 989.315 kilobits per second. That's our throughput calculation. And we also have other metrics or other interpretations of that. We already saw that of our 10,000 bytes of data, we had an additional 108 bytes of header and trailer. Let's all group that together as overhead. So we can say we have an overhead, in this case, of 108 bytes. The throughput was 989,315 bits per second. The original data rate was 1 million bits per second. We can say, therefore, by dividing that throughput divided by the data rate in this case, we get some efficiency. How efficiently are we using our link? 98.9315%, about 98.9% in that case, which is simply 989,315 divided by 1 million and expressed as a percentage. You pay for your ADSL link. You pay 1,000 baht per month for your 1 megabit per second link. You want to make sure you use that link as efficiently as possible. If your efficiency is 98%, that's good. You're using it 98% of the time. But if your efficiency is only 10%, then it's effectively you're not using that link most of the time. You might as well try to get some other system that is more efficient for perhaps the same price. So we care about efficiency, throughput, when we measure the performance of communication systems. In this case, efficiency was simply throughput divided by data rate. When we look into more complex scenarios, it's not so simple to calculate. Returning to our performance metrics, we've just got one more to introduce. Bandwidth is about the set of frequencies that we use to transmit a signal. The data rate is the maximum rate at which we can send bits across a link or across a network. Throughput is the rate at which we can successfully deliver data across that link or network. There's a difference there. Throughput is always less than or equal to data rate. if we have some overheads, and all protocols have some overheads, throughput will be less than the data rate. Sometimes we know the data rate, but it may be hard to determine what the throughput is. If we will work out the throughput, then that's even better. The last metric that we'll cover in any detail is delay. Throughput and data rate are about the speed at which we can send data, but how long does it take to get from A to B? What is the delay in transmitting all of that? The time it takes to transmit the data from source to destination. Of course, the units of delay are seconds. We care about time now. And there are 4 parts of delay in a communications network or a communication system. Transmission delay, propagation delay, processing and queuing. Let's get started on them today. We'll go through more tomorrow. We've seen an example of transmission delay. We had a link which could send 1 million bits per second. We wanted to send 80,864 bits. Therefore, the time to transmit those bits was the 80.864 milliseconds. Transmission delay. How long does it take to transmit all of the bits that you have to send onto the link? That depends upon the speed at which you can transmit, the data rate of your link, and how many bits you want to transmit. If I only had 100 bytes to transmit instead of 10,000, I'd have a much smaller transmission delay, 100 times less. The larger the data we want to send, the larger the transmission delay. So that's the first measure of delay, or the first component of delay in a communication system. How long does it take to transmit data onto a link? Depends upon the data rate of the link and the data size. In this case, it was 1,108 bytes. The next one, which we haven't seen yet, is the propagation delay. How long does it take for a signal to propagate across a link? When I'm talking to you, how long does it take for my voice to get from, in fact, the speakers to your ears? Anyone know? Some waveform comes out of those speakers and reaches your ears. And it reaches his ears at the back as well. When that waveform comes out of the speakers, it propagates through the air, and that takes time. That's the propagation delay of that signal. That depends upon how far between the source and destination. It's going to take longer for that audio to reach the person at the back than it is to reach the person at the front. Not much, but slightly longer. So it depends upon the distance, the physical distance between source and destination. And also depends upon the speed at which that wave travels. In the ideal case, it travels at the speed of light. If we're sending electricity, we can send over cables, it's going to be less than the speed of light, but very fast. For example, well, not for example, we'll write an equation to finish off. if our link in this example was 300 metres. The cable was 300 metres between the two computers. And we assumed in the best case that the speed to transmit a signal was the speed of light. In fact, in physical cables it's going to be less than the speed of light. But the speed of light, from your basic physics, about 3 pi 10 to the 8 metres per second. 300 million metres per second. The propagation delay of the signal is simply the distance, 300 metres, divided by 3 by 10 to the 8 metres per second. Which is what? 300 million divided by 300 divided by 300 million, sorry. Is 1 microsecond. So the time to transmit that signal over a 300 metre cable is 1 microsecond. The time to transmit all of the bits out of the computer at the source A is 80,864 microseconds. So in this particular example, transmission delay is about 80,000 microseconds. Propagation delay is very small, it's just 1 microsecond. So they are two key components of how long does it take to get our data from source to destination. Over a short distance, propagation is going to be very small because the speed's very high. But over long distances, tens of kilometres, hundreds of kilometres, thousands of kilometres to a satellite, the propagation delay can be quite large, and that becomes significant. And that's one of the reasons why satellite internet services are not very good for things like web browsing, because the delay can be quite large. I think it's time to stop, so what we'll do tomorrow is go through a more detailed example illustrating these two components and the other two components of delay. Let's continue that tomorrow.